All right. So in order to build, though, a useful definition, right, not just an intuitive definition, we're going to have to make these phrases precise. What do we mean by get close? And what do we mean by stay close? Okay. All right. So we're going to do this in stages. So first definition. Let L be a real number. Any open interval of the form L minus A, comma L plus A. Okay, and let me draw this. So there's L. And if I do L minus A, assuming A is some positive number, then that's maybe over here. And then L plus A is over here. So how far is it from L minus A to L?
A.
That's A. And how far is it from L to L plus A?
A.
Also A. So would you agree L is in the center of this open interval? Okay, open
Yes.
because we don't include the endpoints. Okay. So any open interval of this form is called an L-centered open interval. Now that is a very long expression, okay? And I don't want to write that all the time. So I'm just going to write, or I'm going to take C-O-I-N. It's going to be called an L-coin. This does not exist in the mathematical literature. This is invented just for you. Okay? This is an L-coin. Okay, and I want you to think about it, right? Like visually here, I could take a physical coin, right? Like a penny or a dime, and I could lay it down with L at the center. Okay, so there's my coin that I draw, or put it down there, right? And there's different size coins, right? There's different size coins, right? So I might have, there's one coin, but I also might have a smaller coin like that. But they're all going to be centered at L. Okay. Cool. Now I started this way because I don't want to use Greek until I have to, because I know people are scared of Greek. Okay, but we need to learn it at some point. So when we're talking about L coins, the size of the L coin, that'll be this radius, right, of the circle, right, which is A. We like to use a specific Greek letter. Okay, and when I say we, I mean mathematicians. Okay, so I'm going to use that Greek letter here, and it's the Greek letter epsilon. Okay, so this is a Greek letter epsilon. Okay, and then I'm going to put this Greek letter epsilon here, and so all these A's are going to get replaced by epsilons. Okay, but it just means the same thing as A. And of course, we almost, well, in mathematics, we will almost always use the convention that epsilon is greater than 0. If you ever write down epsilon is less than 0, you will make mathematicians first laugh and then be annoyed, right? It's like a good joke. Let epsilon be less than 0. You like just say that at a party with mathematicians and they will laugh, I guarantee it. Okay. So that's our first definition. Second definition. So let A be a sequence? Okay. I want to define a tail of A. So a tail of A is any sequence of the form, okay, you start somewhere, right? Like the kth term of A, and then just keep going. Okay, so this bears an example or two. So let's say my A was the first one from the, oh, I don't need parentheses and an underline. First one from the group work. Okay, if I wrote down 3, 4, 5, 6, and so on, right? I'm skipping the first two guys, right? The 1 and the 2. Or if I started at 8, 9, 10, 11, 12, etc. Right? These are tails of A. So think of the sequence, right? Going off to the right, that's your tail. And if you just cut off the head, the first bit, it's a tail. Okay. If I did like 1, 2, 5, 6, 7, ... this is not a tail. There I'm removing stuff in the middle, but I still have the head. And then I do have a tail on the end, right? But I have more than just a tail. That's believable? Make sense? Okay. So I cut it off somewhere, I get a tail. All right. Next, let's go back up. Oh, well, you can do one more thing here. So I have this sequence. I take a tail, and I can ask where all those elements in the tail live, right? And it's possible that when I write them down that they show up in a particular L coin. Okay. So another definition. An L coin contains, okay, so that's the definition here. It's the definition of the word contains a tail of A if every element in the tail is an element of the L coin. Okay, so let's do an example. Okay, so I'm going to put an L coin, right? In this case, it's going to be a 0 coin. Okay, and I'm going to make it, let's go from -1/4 to +1/4. Okay, so this is a 0 coin with radius 1/4. A 0 coin with radius 1/4. Okay, now we had this sequence. I think we called it B sub n. 1, 1/2, 1/4, 1/8, 1/16, etc. And I claim that this 0 coin with radius 1/4, it doesn't contain the whole sequence. Which numbers are not in this 0 coin?
One.
Definitely not, right? 1 is way over here. I mean, I'm not even drawing this to scale, right? 1 is way outside. Okay. How about 1/2?
between 1/4 and 1.
Yeah, that's over here. That's not in the, like here's our zero coin, right? 1/2 is not inside that zero coin. Okay, how about a 1/4? Ooh, it's tricky. It's right on the edge, isn't it? Well, this is where the O is important. Okay, so the O in L coin, right? The O meant open interval. So when we use parentheses, right, that makes it an open interval. What does that mean happens with the endpoints?
They're not
You don't
included.
include them.
They're not included. So actually 1/4 isn't in this interval because it's right on the end, right? So that's not in there either. Okay, but what about 1/8? Well, there's 1/8, and that is in the interval. And 1/16, that is in the interval. And 1/32, that is in the interval. Right? So the entire sequence is not contained in this zero coin, but a tail of it is, right? So this is not contained in the zero coin. But if I take the tail that starts with 1/8, this is contained in the zero coin. Okay. Okay. So now let's go back to our informal definition. Our informal definition for sequence convergence was that the values of the sequence have to get close and they have to stay close. Now, get close. That means you need to be inside, right, one of these L coins. That's what it, like, getting close means you write down some little interval around your limit and you get in there. All right. And stay close, that means you don't leave there. So you get into the L coin and then you don't leave the L coin. But if you don't leave the L coin, that means that you are a tail that's contained in the L coin. So this motivates our formal definition. Okay, so a sequence A converges, that's the word we'll use, to a real number L if, now, okay, we do have to deal with one other thing. Let's say I write down just this one particular zero coin, right? Has radius 1/4. If all of the terms of the sequence were in this interval, is that enough for you to be convinced that it converges to 0? Okay, so what I mean is this, I put here ... which makes you assume that the next one is 1/32 and then 1/64 and so forth. But let's say I told you that that ... didn't really mean that, right? You think it does, but it really doesn't. Okay, there's weird stuff that happens here. However, no matter what weird stuff happens, all of the numbers in this sequence, right, from here on out, will be in this zero coin with radius 1/4. Would that convince you that all of the points were getting close and staying close to 0? If all you knew is that the points were in this interval. So what I'm worried about is this. What if I start drawing more points and they're like here, and then they're here, and then they're here, and then it just like oscillates back and forth between a couple of these points. Back and forth, back and forth, back and forth, back and forth between these two. Is it getting actually any closer to zero at that point? No. So when we say it gets close to zero, that whole notion of close, it's like a moving target, right? Like I put it at 1/4 here, but you're like, no. Eventually you have to get closer than that, right? Like you should definitely at some point get closer than 1/32, right? And eventually you should get closer than 1/64. In fact, no matter how small somebody makes that zero coin, eventually you should get into it, right? So here's our definition. If every L coin, okay, so we need it, anybody writes down an L coin, okay, no matter how small it is, if every L coin contains a tail of A bar, that's going to be our formal definition. If every L coin contains a tail. Okay, so no matter how small somebody makes this L-centered open interval, you can find a tail. You may have to go out very, very far, right? Because the tail doesn't say, oh, you'll cut off the first two. It might be cut off the first billion. Yeah, and then take the rest of them. But every L coin, no matter how small it is, will contain a tail. That's what it means for it to converge to this number L. Okay. This definition will not appear in this form in any textbook. Okay, this is just for you. You're the only ones in the world who know it this way. Okay. The reason why I'm writing it this way is because the ones that do appear in the textbook, including our own, are very complicated in terms of they use a lot of for all this, there exists that, such that this, assuming that, like there's a lot that goes into each one. And I think it'll be a little bit easier conceptually to have this as a formal definition. Okay, and we can talk about things with this language. Okay. Now, of course, a definition is only good if you can use it to prove things. So what I want to do is try to translate this into something we can use to prove something. All right. For example, well, we have this Bn, right? And what did we think was the limit? Whoops. As n goes to infinity, what did we guess it was? So, oh, Brian in the chat says this is somewhat similar to epsilon delta definition of a limit. That's right. I'm really hiding a lot of that, the technicalities of that. What did we think was the limit of this sequence up here?
0.
We thought it was 0. Okay. So to prove that this limit is 0, we need to show that every L coin, which in this case L is 0, so we need to show. So we need to show that every 0 coin contains a tail of, let me just call it B. Okay, fine. I need to take a 0 coin then. Okay, what does a 0 coin look like? Let's draw a picture. A 0 coin has 0 in the center. And then you're going to go over here to 0 minus some epsilon and 0 plus some epsilon. All right, where This distance here is epsilon each way, right? So that is what a generic, like I don't want to prove it for any particular zero coin. Like we know it's true for 1/4, right? If the radius of the zero coin has is 1/4, but that's not good enough, right? We need to do it for every zero coin. So I'm going to write down this generic zero coin that has radius epsilon, right? So somebody picks it, there we go. Now I want to know which tail of B is going to be in this zero coin with radius epsilon. Okay, well, that feels difficult. Okay, so let's ask what we're really trying to do. We know that the B sub nth term is, well, depends, right? If we start at 1 or 0, let's use the one that starts at 0 so that we have the easier formula. All right, so we know that B sub n is equal to 1 over 2 to the n. Okay. Is there some number that I could put up here to guarantee that 1 over 2 to the n will be in this interval? So, because I'm looking for a tail, right? So I need to go out far enough. So how big must n be such that 1 over 2 to the n is in, well, okay, 0 minus epsilon, right, is just negative epsilon, and 0 plus epsilon is epsilon. So is in negative epsilon to epsilon. Okay, this feels still like a challenging question. So let's think about a few things. First, is my sequence ever going to be on the left side of 0? No, right? This is always positive. Okay, so 1 over 2 to the n is always positive. So I don't really have to worry about that. And in fact, it just has to, is it ever even going to be 0? No, right? Definitely greater than 0. So we actually could have written here like 0 to epsilon. Okay, now what does it mean? Well, let me write this on the other side. What does it mean if you're in this interval? That means you're bigger than 0 and you're less than epsilon. So the real question is, how big must n be such that 1 over 2 to the n is less than epsilon? Well, this is actually the type of question that we solved back in the numerical integration section with Simpson's rule, where we said things like, how big does n have to be so that the error in Simpson's rule we know is less than, 10 to the negative 5 or something, right? We have to solve for n. That's the real thing now, right? Solve for n. Okay. Well, one thing I could do is just swap the 2 to the n and the epsilon, right? I'll multiply by 2 to the n and divide by epsilon. And everything's positive, so I won't change the inequality. So 1 over 2 to the n less than epsilon is equivalent. Okay, I'm going to multiply by 2 to the n and divide by epsilon to 1 over epsilon is less than 2 to the n. Okay, how can I get rid of, like I have an n, that's what I want, but I have a 2 to that power. How do I get rid of that 2?
Log 2, log
Yeah,
base 2.
let's take the log base 2 of both sides.
Also, Dr. Klesser,
Yeah.
in the case where the sequence can be negative, would it be possible just to take the absolute value?
Absolutely.
Okay,
Absolutely.
and then just evaluate like the absolute value is less than epsilon?
That's right. That's exactly what's going to happen. So here I would get the log base 2 of 1 over epsilon is less than n. And that does it. This tells us how far we have to go out. Whatever, like, okay, so somebody give me a really, really, really tiny number for my epsilon. You can just write it in the chat. 0.005. Okay, so somebody says, I want to know how far out you have to go so that everything is within 5/1000ths of 0. Well, I can take the log base 2 of 1 over 0.005, which incidentally, I believe is the log base 2 of 200. All right, and okay, so I can go into, I just go into Desmos. I'll see if it does log base 2. I'm curious. Log base 2 of 200. Hey, 7.64. Okay, so this is about 7.64. So we know that n has to be greater than 7.64. Okay, so how about we let n equal 8? Okay, remember n is the exponent though. Okay, so let's see, when n is equal to 8, what does the tail look like? So we're starting at 1 over 2 to the 8th power, 1 over 2 to the 9th power, and so forth. Okay, 2 to the 8th power, that's what? 1 over 256? And yeah, 1 over 256 is less than 0.005. Which I only know because I know 0.005 is 1 over 200. Because I'm like, you know, smart or something. No, it's just because, you know, if it was 0.001, it'd be 1 over 1,000. And so this is 5 over 1,000, which is the same as 1 over 200. Okay, so that's how we can do it. Now, imagine you didn't know about the log base 2. Or any, I mean, if you didn't know log base 2, you could just take regular log, right? Like natural log. All right, so you could go, so what if we did natural log? Then you know ln of 1 over e, or epsilon rather, is less than ln of 2 to the n, which is n times ln of 2. And then you can divide by ln of 2, and you'll get ln of 1 over epsilon over ln of 2 is less than n. Okay, so you could do it that way if you didn't know log base 2. And if you didn't know any logs at all, then this gets a lot harder, yeah? It's much worse. Which is actually the point I'm trying to make, which is, okay, this is a miracle. Whether you use log base 2 or you take the natural log, it's a miracle. And there are going to be times where finding that miracle can be very challenging. All right. Speaking of challenging, I want to send you back to your breakout rooms for the last bit and let you work on your own problem with a proof. Any questions before I send you away though? Because this is pretty big.
How do we use this to show, or is it intuitive to use this to show that a sequence diverges?
That's a little bit different. So if you want to show, so by the way, like let's just write this down formally so we have it. Definition, a sequence A bar diverges if A bar does not converge to any real number L, or I'll just say any real number. Doesn't matter what I call it. I don't even really need to call this A here. I could just say a sequence diverges if it does not converge to any real number. So Brian is asking, right, about how do you then use this to show that something diverges? Okay, so let's go back to this definition. A sequence converges to a real number, L, if every L coin contains a tail. So for this not to happen, that means that there must exist an L coin that does not contain a tail. Right? So, for example, go back to our very first sequence of the day. You all thought that this diverged, right? You all said that the limit was infinity, which is not a real number. Okay, but in the chat, Arthur was telling me he thinks it converges to 3. I'm joking. Okay, Arthur didn't really write that. I'm just giving him a hard time. And he's he's like, oh my God, I thought he meant that. Okay, so claim the limit as n goes to infinity of an is equal to 3. All right? And 3 doesn't really matter here, right? Pick any number you want. Okay, is this true? Like, do you believe this? No? Well, why not? Well, here's like 1 is just your intuition. It's not getting close to, I mean, it gets close to 3, right? Because look, 1, 2, 3, boom, that's as close as you can get. But what's the problem? It got close to 3, but what's the second half of that informal definition? Not only does it get close, it has to
Stay close.
yeah, exactly. It has to stay close. And well, that's the problem here, right? It doesn't stay close. So here's how we use the definition to prove this, right? That this fails. So there's 3. Okay. Pick a 3 coin, any radius. What radius would you like, Darian?
4.
4. Okay. So there we go. So 3 to 3 minus 4, which is -1. And then I go up by 4. Whoops, 3 plus 4, that's 7. Okay, so there is my L coin of radius 4, or 3 coin of radius 4. Okay, if this claim is true, for the claim to be true, this 3 coin of radius 4 must contain a tail of A. Some tail, right? You may have to go out really far, but eventually it should contain everything in the tail. Okay, and what's the problem here? Well, let's see. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, ... What's happening to these points? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I go out far enough, they're not in that 3 coin, are they? They leave it. For n greater than or equal to 7, right? 7's not even in there. It's right on the border, but it's not in there. For n greater than or equal to 7, a sub n is not in the 3 coin. Okay, so no tail can be, therefore, thus no tail, because the tail just says go make n bigger and bigger, right? Until you get it where you want it to be. Well, you're just making it worse the longer you go. No tail is contained in this 3 coin. Thus, the limit as n goes to infinity of a sub n does not equal 3. All right, but the same type of argument will work with any number, right? And any whatever L you pick, any L coin, eventually you're going to leave it because this thing just keeps growing to the right. Okay, so it doesn't work.